Hi and welcome, and for all my new viewers, welcome to my channel TM Electronics, and not just TM Electronics but TM Electronics and more. As promised in my previous video, I will show you how to upgrade these eBay LED lights. If you didn't watch my video, I recommend you do it now. In short, for those who didn't and who will not watch it, design of these lights is really bad, and not just that, they could potentially be really dangerous, and then they can literally kill you. And before we just go into it, let me just show you uh, what we are gonna do today. So we will improve safety. That's an absolutely necessary. Uh, and we will also improve functionality. We will get rid of annoying flickering that interacts with your camera. That's like a black and white pattern that goes up and down, and it's making things really annoying when you are recording something. And when we will improve that, as a consequence, we will also improve the other performances, like we will get a stable power consumption across all voltage range that is to be expected on our mains voltage, and that also means that we will get a predictable heat dissipation. And in the end, we'll just check how good or how bad is the uh, heat transfer between the aluminum PCB and aluminum heatsink, and if needed, we will fix that. How we're gonna do this? In terms of safety, we'll do just a simple cable management, not like professional one, but it will do. We'll improve the grounding. If you look at my previous video, the grounding was made terrible. It didn't even make a connection with the chassis. So we'll improve that. And as I said, in terms of functionality, no more flickering, stable power consumption, and better heat transfer. We'll measure that, and if needed, we will improve that also. First, I will do like a simulation in LT Spice. Maybe you're not familiar with this program, but I will just show you reverse engineered schematics of the LED, and we will simulate it. Secondly, I'm going to do some measurements to see if the reality confirms our simulation. And then we will do the simulated upgrade, and if it went well, we will do also a real upgrade on the LED that we got. In the end, of course, we will do tests, final tests, final test to check if we did anything with all that effort, or we just wasted our time. I hope not. So let's go. And that's the actual schematic of our LED lights. On the right we have a power supply that's voltage. It's going through the diode bridge, and we have 10 nanofarads of capacitance. That's nothing. I added R1 just to measure the summered current through all of the LEDs. And then we have 5 strings of the serial connected LEDs 3 times. On the end we have low side current limiters. I just gave 100 milliamps in there for simulation purposes. And if we simulate this, let's run it. Let's first check the voltage, okay, and the current. As you can see, well, it stopped exactly at the 1.1 amps. That's 11 times 100 amps, 100 milliamps. And if we pick one LED, we can see that light is pulsed every 10 milliseconds, and then just current limited. that should be around the same on the bench when we will measure the real thing. So let's go.
Okay, here we are. Even though I covered the LEDs with black tape, we can still see the flickering. And I don't have isolated probes, so we will do like a mathematically calculated difference. We have a full bridge rectifier that's about something above 300 volts. Okay, just for fun, let's measure the current. I think that 150 watt it's a bullshit. Let's just check what we have on the mains. 500 milliamps. And what that gives us. For the completeness, let's also measure the AC voltage. 244 volts, so it's pretty high right now. And yeah, instead of 150 watts of energy, that light gives us only 120, and that's on the 245. So on the 220 volts, that will give us, let's say, 110 watts. So nope, this light ain't 150 watts. Don't have isolated oscilloscope probe, so what's the easiest way to measure the flickering? I've made really simple circuit. It's just a photo transistor and pull-up resistor. The oscilloscope will show us an inverted signal because it's pull-up, and when the photo transistor catches the light, it will go down, and we will see a pattern like a PWM signal. So let's try it. Well, I'm sorry, I will single capture that and I will show you on the oscilloscope what we get. We have to watch the minus dute. It's a 71.64%. It's really simple. We will just add one big S capacitor in there and that. But we have to be careful because with the capacitor we will get like a 100% PWM, and that will increase our power. We will try to limit the power to 100 watts, and that's gonna be enough.
I tweaked our circuit a little bit just to achieve the same duty cycle as we get on the real light. What we're gonna do, we will increase our capacitance just to remove any duty cycle at all. So you want to get 100%. And in the end, on the real light, we will have to change the limiter resistors that are on the drivers, the current drivers. So we will lower the power consumption of the light. But that's just the last step. So let's begin. We'll have to take it into account that we will have to give 400 or 450 volts capacitor. So they're not cheap and they're big, but let's see what we need. If we insert 100 microfarads, how we are doing? We are doing excellent. 22. That's not much. No, we still get exactly the same result. 10 micro. Okay, now we're starting to see the juice is just a little bit too low to achieve the perfect linear drive. But I will check what I have in stock. Maybe I will take the capacitor from some old electronics. If I will find 10 microfarad capacitor, I will try this. Let's go to the bench.
Well, we should have used heat shrinking tubes for protection. I will just cover it with some silicone. It's okay. The wires won't go anywhere. All we have to do now in terms of functionality, we have to change these 11 resistors. We will have to raise them for, I don't know, 10-20%. Right now they're 15 ohms, and we will try with 20 and we will see what power do we get. Voltage is 242 and the current is 540 milliamps. So that's 130 watts. Is that too much? I don't know. Oh, and yeah, of course the power of the light will change with the voltage. Of course it will, but the power of the LEDs, only LEDs will stay the same over whole voltage range, and that's what we want, because the LED will degrade at 70-80 degrees. They will degrade with time, but the drivers, they're made for the 175 Celsius, and they will be just fine. So I don't care about the drivers, I care about the LEDs. It's 77 on the middle of the PCB and 66 on the aluminum heatsink. So that's not too bad. The heat transfer is okay, but the temperature on the PCB, it's a little high. Yeah, we can live with that, but you see the problem. So the LEDs are randomly dying. A lot of effort went into a repair, but you see that these lights are terrible. So that's actually a first use. That is the first time that the LED is on for more than few minutes. And yeah, the few of them already died. So do yourself a favor and do not buy those cheap eBay LED lights or floodlights. I'll maybe buy the new cheap LEDs and replace the dead ones, but not the best light. that's for sure. And for a safety improvement, we will use just two simple solutions. First one is cable tightening. We're gonna just pull some more cable inside, and we'll just use the ferrite ring. We are using those for AMC compliance problems. So just one turn it, and now if we try to pull the cable out, there is no way. I don't want to drill another hole to the heatsink. We'll use the same hole, but I will just add better screw and the star washer that is used for these purposes. So the connection between the input cable and the chassis will be much better. So let's just screw that in. Oh, that's it. That will not move anywhere. Just a quick check. Yeah. Let's just solder these two wires back and assemble the lights together. And that's it. Let's make a wrap on this video and see you next time. I hope you enjoyed it. So have a nice day and see you next time. Bye.